Hello. So in one of the previous videos we already started discussing how many variables you shall add to the regression model, and this video is devoted to specification bias in models with multiple independent variables. I will explain the nature of this bias using the following regression model. The dataset is attached in materials for this lecture. So child mortality rate is the dependent variable. We take this value for 2018, and in our case index I stands for country. So we estimate the model for cross-sectional data. FLR stands for female literacy rate in the same period. By the way, we expect that beta 1 has a negative coefficient due to the fact that higher female literacy rate is expected to decrease child mortality rate. There is a lot of literature devoted to this topic, but very intuitively you can explain the relationship between those variables. So if females are more educated, then they have more control over their reproductive rights. They are able to control the number of children and provide better health care for their children. They are more aware of the methods used to prevent child mortality, and so on. And GDP per capita in year 2000 stands for the proxy for the level of economic development and quality of life. I believe this is pretty intuitive. So if the country is wealthier, then child mortality rate shall be lower. So both of those coefficients are expected to be negative. So we run the regression model in Gretel. Just give me a second. I just want to do the same because we will have to use the output of this model in order to run a test. So yeah, here is the regression model. As you can see, in line with our intuition, the coefficients are negative and they are statistically significant. However, it's possible to hypothesize that some of those variables was added by mistake. So again, it's very formal, but you can run the test for omitted variable. I can exclude GDP per capita variable from the regression model and estimate the reduced model. So as you can see, at the result, female literacy rate is still has a negative and statistically significant coefficient. However, the value of this coefficient and the value of intercept are different, which is a natural thing because those variables are at least to some extent correlated. So, for this test, null hypothesis says that regression parameter for GDP per capita in 2000 is equal to 0. Because p-value of the test is smaller than 0.05, we can reject zero hypothesis. So basically it means that this statement is not true, and the alternative hypothesis, which says that for GDP per capita 2000 the value of parameter is different from 0, is true. So here you can just see the output of the restricted model. You're gonna need it a bit later. Okay, so this is the test you can use in order to verify whether the variables added to the regression model are indeed statistically significant. They should be added to the regression model. And there is also something called joint significance test. So in joint significance test, you have to analyze statistical significance for several variables. So null hypothesis says that the coefficients are equal to 0, and alternative hypothesis is that at least one coefficient is not equal to 0. So in order to do this, you have to take sum of squared residuals for the unrestricted model with all the variables added and the restricted model. Q stands for the number of restrictions, number of variables excluded. In our case, it's equal to 1. N stands for the number of observations. K stands for the number of variables. So using this formula, you can calculate F statistics. Of course, in order to make any conclusion, you also have to calculate p-value. For this purpose, you can use Gretel, but I leave it for you. You already know how to do this. And finally, another thing to discuss in this video, the final one, is related to adjusted R-square. So I think it's pretty intuitive that if you add more variables, which can potentially explain the variation in the dependent variable, then the value of R-squared should be higher and higher. However, you should also account for the fact that not all of those variables can be justified. So, of course, if you add more, it kind of improves the performance of your model, but at the same time, you are doing this by including additional variables. So, adjusted R-squared is calculated according to the following formula. As before, K stands for the number of variables, N stands for the number of observations. Is actually the value of R-squared adjusted for the number of variables you use in your model. So you can easily see, based on this estimation output, that R-squared is always bigger than adjusted R-squared if the number of explanatory variables is bigger than 1. Of course, in our case, we have only 2 independent variables, not accounting for the constant term. That's why the difference between those 2 indicators is not that noticeable. However, if you add more and more variables, it will become more and more significant. That's why when you analyze goodness of fit of your model, it's a good idea to concentrate on adjusted R-squared instead of R-squared. Okay, so that was it. I really hope you enjoyed this video and see you in the next one.